Quantum computers can work exponentially faster than other kinds of computers. And once a large-scale version of this computer exists, it'll probably break all the most common encryption tools we have. It could also speed up the discovery of new materials by performing simulations at speeds that are hard for us to even understand. Quantum technology could create trillions of dollars of value within the next decade, according to a recent McKinsey report. And one of the leaders in this space is Hartmut Neven at Google's Quantum AI Lab. He's a scientist best known for his work in face and object recognition and for his contributions to quantum machine learning. Throughout this series, we'll be featuring the stories of breakthroughs and other key moments in emerging tech, as told by those who witnessed them. I'm Jennifer Strong, and this is Shift.
Now here on the steering column is a device called Auto Cruise. You simply set the speed you want.
Self-driving robo-taxis are already on the road in 2 U.S. cities.
As the disk rotates, a mirror reflects the light in the way that depends on how the signal was recorded.
This is the 100 terabyte I present to you Electro, the Moto Man.
Ladies and gentlemen.
I would say that one of my greatest skills is my ability to interact with humans.
This episode, it's the latest installment of our oral history project, recorded at the TED Conference in Vancouver, Canada.
As amazing as computers seem today, they seem to be pervasive and seem to be able to do everything. It's actually not true. There are many important problems that we know ordinary computers will never be able to solve. I'm Hartmut Neven. I'm a vice president of engineering at Google, and I'm the founder and lead of the Google Quantum AI Lab. Our objective is to build a useful quantum computer. And quantum computers are new tools that allow us to solve more problems, but they're not almighty either. Even for quantum computers, there are yet more difficult problems that quantum computers can't solve either. Training, I'm a physicist, also spent many years in neurobiology labs, and actually it was through an NPR radio show. So when I joined Google, I was initially responsible for the visual search team. And at the time, computers weren't all that powerful. So there was a transformation of the images we would do. It was not possible to transform a whole image. We could only transform parts of it. And of course, then it's a little bit chicken and egg. You know, you want to recognize what's in the image, but you can only analyze part of it really well. So where do you put your attention? So that was the state of affairs then. And then I heard a report in NPR radio about quantum computing, and I misunderstood what they were saying. But it appeared to me that the upshot could be that this image transformer wanted to do could be done much better on quantum computers. That was my initial being drawn in. And computer vision still today is done with machine learning methods. And machine learning, as the name suggests, is based on training systems like we train children. We give examples, like, look, this is a face, this is not a face, this is a face, this is not a face. And then eventually the system learns to detect a face in an image. But if you look at this process a little bit more abstractly, you would, or a mathematician or computer scientist would say, the training of, say, a neural network is formulated as an optimization problem. It has been proven that quantum computers will be better, faster in solving optimization problems. So there you put one and one together. It said Google wants to be an AI-first company. AI is really being good in machine learning. Machine learning is really applied optimization. And here is a computational tool that does optimization better. So if you want to be first in AI, we better have access to a quantum computer. around that time, there was one company called D-Wave that was the first company to offer access to commercial quantum machines. They were not a general-purpose quantum computer, but they were a special-purpose quantum computer to do optimization, exactly the thing I was interested in. And I read about this company in the news, and I was tracking them and figuring out, are they for real? I thought quantum processor is so difficult to build. How come they can already sell some? And one day the CEO, a founder, Jordi Rose, he called me. And I'm from this company, D-Wave, and I was wondering whether you can use our processors for doing your image recognition work. And it's so funny you call me, because I keep tracking your company and I'm asking my friends whether you are for real or trying to understand what you're doing. So this became a nice interlinked friendship. So Jordi was really more interested in AI than in quantum. So I taught him a lot about AI, and in turn he taught me about quantum computing. So we had this really nice match, and that led then in 2007 at a trade show called Supercomputing. So at Supercomputing 2007, we demonstrated on the show floor an actual image recognition algorithm implemented on one of the D-Wave machines. So that was the first pattern recognition algorithm ever run on a quantum machine. Going forward a little bit, we also did the first implementation of a quantum machine learning algorithm. And that together gathered enough attention within Google that the decision was made, okay, let's start a quantum computing effort, the quantum AI lab at Google. You need hardware for this. Quantum computing is a hardware game. So we started with leasing a D-Wave machine. By that time, they had sort of several hundred qubit special purpose quantum optimizers. So we leased one of those machines and we thought we are off to the races. But then our nascent team, mainly consisting of theoretical computer scientists, they proved that the D-Wave process, which the technical term is quantum annealing, it's a special quantum enhanced optimization algorithm, that this could be emulated on classical computers at a significant overhead cost, but at a fixed overhead cost. What do I mean by fixed? Normally what we are looking for in the race between classical and quantum computers is what we call a scaling advantage. A scaling advantage means that the advantage gets bigger the bigger the problem gets. The example of unstructured search, this tall closet with 1 million drawers, and a classical algorithm would need an average 500,000 steps to find a single item in one of the drawers. And amazingly, a quantum algorithm would only need 1,000 steps. But this difference depends on how many drawers there are. So the advantage gets larger and larger the bigger the closet gets. The bigger the problem gets, that we call a scaling advantage. And then to the chagrin of D-Wave, and also to our chagrin, is we realized this quantum annealing process would give us only a fixed factor independent of problem size. And we thought, oh damn it, that's scary, because you can chip away of this cost and you can't make up for it by just going to bigger problems. So we decided, okay, we need to build a universal quantum processor. And then it was around 2014. And then 2 years after the foundation of the Quantum AI Lab. And then we decided, okay, we will build our own hardware at Google. When I started with D-Wave, it was hugely controversial because people didn't believe their machines were using quantum effects. So we helped them out in the sense that we cooked up a special purpose problem, a benchmark problem, and this annealing algorithm, it has a classical version and has a quantum version. And pretty much every expert in quantum computing at the time would say, oh, they do the classical version, it's not really the quantum version. And then, this was actually one of my first-hand contributions, I invented a problem to say, look, this problem should go really quick if it's a true quantum annealer, but should take forever if it's a classical annealer. And we tried this, and there was this tremendous difference, a factor of 100 million times slower for the classical annealer versus the quantum annealer. So then even the big skeptics said, yeah, okay, we admit this is a quantum processor. But it was sort of, I think it's called a Pyrrhic victory, because we could show that, yes, it's quantum, and it does faster than the classical annealing algorithm, but there were yet other algorithms, also classical, that were faster than both. So we established it's quantum, but also established there's no speed up yet. With this lesson learned, when we started our own hardware effort, I thought the first thing we need to do is to unequivocally show on a problem, and it doesn't have to be a practical problem, just some problem, that a quantum computer does very fast and the best classical machine would just take forever. And that was the result in 2019. There we published this result. We don't call it this, we call it beyond classical computation at the time, maybe just for historical reasons. The paper calls it quantum supremacy, which was a term of art. We didn't invent this term. That result established that there's a benchmark problem. And I always like to say, this is not a problem anybody has in real life, but it was a well-defined mathematical benchmark problem. Our chips could do it in minutes, and if you would have had, of course nobody could do this, run this problem on the top supercomputer at the time, then it would have taken 10,000 years for this big machine. Once we published this, we had a huge target on our back. The classical computer scientists would say, wait a minute, you have not used the very best algorithm we could possibly come up with. And then there was this worldwide effort. This history should be written one. And there were researchers from Caltech, from Alibaba. There was like many top academic institutions around the world, like hundreds of people working on making the classical algorithms better and showing we can do this too. And they succeeded. They tremendously improved by 10 orders of magnitude. I would not have thought. By 10 orders of magnitude, so this is, for those who don't know, a 1 with 10 zeros. That's a factor by which the speed of the classical algorithms was improved. And fortunately, we already said in our Nature papers, like, look, we tried our best. Like, our best algorithms, it's 10,000 years on a supercomputer. But we predict others will try more and they will bring this time, like always, software gets better and better. But because we could prove that there is a fundamental exponential scaling difference, that yes, by the time they have the better algorithms, our chips have improved and you can't beat an exponential. Eventually, you will lose out in terms of speed up. We now keep repeating this benchmark. Every 6 months we run it. And the last time we did it, I think, was November or December last year. And now using the latest and greatest software that was developed, and this has now stalled. You can improve algorithms, but eventually they're at their best. They can't do any better. Hardware, of course, is also getting better. People build larger, better supercomputers, more GPUs in there. So today you take the best classical software and the best classical supercomputer, which is Frontier, and pit it against our latest, cleanest, lowest error rate quantum chips. And now what used to be 10,000 years has become 1 billion years, despite all these improvements. So that really shows that quantum computers grow in power in a way that classical machines can't match, at least for certain problems. Today, our gate operations have an error rate of 1 in 1,000. The way to think about it is every 1,000 operations, you will crash your machine. So your poems are limited to just 1,000 letters. It's not much. You can write a little haiku, but not a novel yet. But eventually we want to write novels or write complex quantum algorithms. So we need to get to lower and lower error rates. And quantum error correction is the technology that will allow us to do this. And if you want to make things more reliable, you introduce redundancy. Say you want to have an airplane that takes you safely over the ocean, Instead of using a single engine, you use 2 engines, or you give it 4 engines, and that's safer. And in the same way, quantum error correction works by combining many physical qubits to one logical qubit that then will work more reliably, more accurately, and then the error rates come down, say 1 in a million. That's our next milestone that we hope to reach in the next few years. The next step is to have one long-lived logical qubit, and that's composed of many physical qubits, and that has an error rate of 1 in a million. And once we have this one really good quality logical qubit now, next phase will be to make this a little bit cheaper, because the first one would be too expensive to just say, oh, I want 1,000 of them, the machine, or 10,000 of them, that machine would be too expensive. So we'll have to do a little bit of value engineering, make it cheaper, meantime still better. And then when we like it enough, then we will just stamp it out and say, okay, let's have a machine with 100 of these logical qubits, or 1,000 or more. And the current endpoint of our roadmap, which we hope to achieve by the end of this decade, would say we want to have 1 million physical qubits on our processor, which would translate into 1,000 well-protected logical qubit by the end of this decade. Richard Feynman famously noted, nature is not classical, damn it, and if you want to accurately simulate nature, you better make it quantum mechanical. So this is today called quantum simulation. It's a simulation of systems where quantum effects are important. And that's typically always the case when you do some nanoengineering. So better batteries, better solar cells, better desalination plants, nuclear fusion reactors, small drug medicines, or pretty much all pharmaceutical problems, material science challenges like coating of airplane wings that makes them not rust or have less air resistance, and huge amount of problems where quantum effects ultimately play a role, and you can't properly model it on classical computers, but where a quantum computer would be a marvelous tool. So that is the baseline killer app. Then coming back to optimization, this roller coaster has continued. You can always accelerate the solution of optimization problems with quadratic scaling advantage. So that's always there, but quadratic is not as much as exponential, and there's a big overhead quantum computers will incur when we do error correction. So you would have to go to pretty big problems sort of before you reach this crossover point where quantum computers will be better for optimization, hands down. But that's maybe 15 years out. This is not the first application. So we have been working really hard. Can we not find examples of optimization problems where the speed up is more, or the scaling advantage is more significant, like exponential or to the power of 4, a quartic instead of a quadratic speed up. And indeed, we have found such things. And that's quite relevant for many areas, including AI. So that's another bucket of useful applications. And then my personal interest is what quantum computing or quantum information science has to say about human consciousness and how it comes about. I've formulated a conjecture that essentially says quantum processes create conscious experience. Other people, most famously Roger Penrose, has said this before, but I modified it a little bit. Roger Penrose said a conscious moment occurs when a quantum mechanical superposition state collapses. But I think this idea has problems. It's better to say a conscious moment arises when a quantum mechanical superposition state forms. And the interesting thing is, normally when you talk about or think about the phenomenon of what creates consciousness, you are in the realm of philosophy or even religion. But now we brought it into the realm of experimental science. This conjecture can be tested experimentally, and we have started to do so. Maybe I leave it at that.
This episode was produced by me and Emma Silikans and mixed by Garrett Lang, with original music from him and Jacob Gorski. Thanks for listening. I'm Jennifer Strong.
From PRX.